So one of the interesting quirks of runtime organization, typically associated with the hardware quirks, is the issue of memory object alignment. So what is memory object alignment? Well, it basically means that the objects should be inverse. So first of all, it's a hardware quirk that often has significant performance implications, and sometimes it can even have correctness implications. So we're going to see that in more detail. So here is the exact problem. So memory is usually byte addressable, which means that you can name any one byte in memory. So I could say byte number 100, and that basically is going to be I'll have some value, a byte value at address 100. Similarly, I could say byte number 101, and I will have a byte value at address 101, and so on. Notice that it's not bit addressable. For example, I couldn't say, give me bit number 801. That just doesn't make sense. The way I'll access bit number 801 is basically, I'm going to first have to access byte number 100, because the memory is not bit addressable, but byte addressable. So I have to convert the bit address to a byte address. So I first convert it to byte address 100. Then I have to read the whole byte in one go. And then I can, maybe look at the second bit to look at bit number 801 and so on. Question is, but from the memory's perspective, you can only access it at minimum of byte granularity. Okay, so a memory is usually byte addressable, but often multi-byte accesses are required for many typical operations. So for example, an integer in C, an int variable, is typically implemented using 4 bytes. And so if the memory only supports single byte operations, then if I want to read an integer value, then I would have to do 4 different memory accesses to get each of the 4 bytes of that integer, and then I'll have to string them together to make an integer. Well, that could be option number 1, but that would be really slow, because I would basically have to go to the memory 4 different times. And that's unnecessary, because the interconnect between the CPU and the memory has a long latency. Let's say it can have a latency of around 100 nanoseconds. So if it takes 100 nanoseconds to send a message to memory and bring it back, so round trip is 100 nanoseconds, let's say. But the pipe is pretty fast. So once I send a message, multiple messages can come together, and so it takes 100 nanoseconds to get 1 byte. It takes 100 nanoseconds to get 10 bytes, right? So it's, even though the latency is high, the bandwidth is also high. So I can get multiple data in one go. And so memories typically support multi-byte accesses to make things more efficient. So instead of, if I want to access an integer, I don't have to make 4 round trips. I can just do it in 1 round trip. So I just say, give me 4 bytes starting at this address. And so all the 4 bytes are going to come back in 1 round trip time to you. So you just pay 100 nanoseconds for the entire 4 bytes. So this is, so you can read 32 bits of 4 bytes in one go. But often memories have some restrictions on what 4 bytes you can read in one go, of what 8 bytes or 16 bytes. I'm just using 4 bytes as an example. So for example, memories may have alignment restrictions. So for example, they may allow you to read 4 bytes starting at address 100 in one go, but they may not allow you to read 4 bytes starting at address 101, because 101 is not aligned to a 4 byte boundary. 100 is aligned to a 4 byte boundary, but 101 is not aligned to a 4 byte boundary. And so why would memories have this kind of a restriction? Well, that is just so that they can make their own implementation faster. So memories would typically say that if they allow only aligned, a memory designer would say that if I allow only aligned accesses, then I would be able to make the typical case of accesses faster. And also, it's not just about the main memory, but also the caching hierarchy. So these restrictions allow hardware designers to implement faster memories. So because it's more restricted, you will need less circuitry to do the calculations and things like that, and it becomes easier and faster to generate data for aligned accesses than unaligned accesses in many cases. So some architectures like PowerPC would disallow unaligned accesses. Other architectures like x86 would allow unaligned accesses, but they will have slower speed, or they would allow unaligned accesses only for certain opcodes and so on. So for example, you can access 4 bytes in one go starting in address 101, but that would be slower speed. But if you access it starting at an aligned address, so 100 is an aligned address for 4 byte access, 101 is an unaligned address. So for aligned addresses, the access will be faster, maybe on your machine, and unaligned it will be slower. And there are examples of such machines as well. Also, there are some examples. So also, for example, x86 instruction set contains some opcodes which will work only for aligned accesses, whereas there are some other opcodes which are slower, which will work for both unaligned and aligned accesses. And so if you want to use the faster opcode, it would be better if the accesses were aligned. Now, that's a lot of low-level detail of how you should be, how can one access memory, and what is the correctness requirement and what is the performance requirement associated with alignment. But when we write our programs, we don't want to be bothered with all this. We just write our program saying, okay, I want an integer variable, and it's up to the compiler maybe to figure out how it wants to give, what address it wants to give to that particular variable. And hopefully the compiler is going to make an intelligent choice so that most of the accesses are going to be aligned. Or if I'm compiling for an architecture where unaligned accesses are illegal, then all the accesses should be aligned. So what are the implications for the compiler? So for example, it may need to be careful while allocating objects. So for example, allocate a 32-bit object or a 4-byte at a 4-byte aligned address, or a 64-bit object at an 8-byte aligned address, and so on. Okay, so one can be careful. What does it mean? So let's say it's a global variable, and recall that for global variables, the compiler explicitly identifies what address it's going to be stored at. That's in the data region, that's statically allocated. So when it's giving an address, it can figure out what is this type of this object. If it is an integer, then it should give it a 4-byte aligned address. If it is a 8-byte double, then it should give it an 8-byte aligned address, and so on. So that's only for the global variables. What about, let's say, local variables or heap allocated variables? So once again, the same thing applies. So when you have a local variable on the stack in the activation record, if you're allocating a local variable, maybe you won't need to have some amount of padding to be able to identify the correct legal address or desired address for that particular variable. So let's say I have an integer variable which is a local variable in my procedure body. Then whenever that procedure gets invoked, the activation record should allocate enough space not just for the local variable but also the padding required so that it becomes correctly aligned. And that can also sometimes mean that different activations of the same procedure take different amount of space, because maybe the first activation was such that it already gives the local variable an aligned address, but the second activation of the same procedure gives it an unaligned address, and so padding was required. And so the activation record of the second invocation of the same procedure has different size from the activation record of the first invocation of the same procedure. All right, so we're going to see this in a little bit more detail with an example. Also, use padding for compound objects. So typical languages have compound objects. For example, C has the notion of a struct, C++ has the notion of classes, and almost all languages have the notion of objects, classes, compound objects. And so let's look at the example of C. So in C or in C++, so let's say in C++ I define a class foo. Then I could have, let's say 2 fields in it, int I1, char. Let's say I have 3 fields in it, int I1, character array S of 5 characters, and then integer I2. Now, the compiler knows that I1 and I2 are integers, and so it's very likely that in the code I'm going to access these variables I1 and I2 in one go. So for example, I would say I1 is equal to I1 plus 1. That's going to have to read all the 4 bytes associated with I1 in one go. And so that's going to be a very common operation. And so maybe the compiler wants that I1 and I2 should both be allocated at 4-byte aligned addresses. But that means that if both I1 and I2 are allocated at 4-byte aligned addresses, but the middle field here is a 5-character array. And so the only way this can be achieved is only if we add some padding. So for example, the compiler may want to introduce a pad of 3 bytes between either the first integer and s, or between s and the second integer, so that I1 and I2 can remain aligned, and I can have character array of 5 bytes s in the middle of both of them. And so what this padding bytes are going to do is it's going to take some extra space, in this case 3 bytes, and so that is that is wastage of space, you may think, but this space is useful if the machine has alignment restrictions, either because of correctness reasons or because of performance reasons. And typically 3 bytes, even if it is for performance reasons, 3 bytes would be typically a very small price to pay in space to have faster accesses to my integer objects. Here's another example of what may be required by the compiler to be able to deal with alignment. So let's say I have this C code where I have this local variable called x of type integer. Now, actually C has this interesting requirement that all addressees of, so C is a low level language, so it basically can say, it also has alignment restrictions on how variables of certain types should be allocated. And so C requires that all variables of type integer should be 4 byte aligned. And so what this means, for example, when I'm implementing this, when I'm generating code for this, when the compiler is generating code for this, is that the first few instructions of foo could look like the following. It's going to, let's say the stack pointer is denoting the current stack, top of the stack. So the first thing it does is it ANDs the address of the stack pointer so that it becomes aligned with a 4 byte boundary. Notice the mask of this AND is basically all ones except the last 2 bits, which are 0. And so ANDing with the ESP basically means just decrease ESP by just the right amount so that ESP now becomes 4 byte aligned. And now you basically subtract 4 from ESP, and this is the region where you're going to store the value x. And so using this computation, using this AND operator with a mask that has the last 2 bits to be 0, one can align the stack pointer. In other words, I'm aligning the place or the activation record so that I can have aligned allocation for my integer object.